Hello everyone, my name is Pauline Mbasani and I'm going to be taking you through the scalp and pathology detection using machine learning, and I assume that by the end of the presentation we shall have a clear understanding of how I approach this problem and which models I used and why I used these models. So first, we're going to start with the background and introduction. In Africa, we have fewer than 40 registered trichologists for a population of about 48 million people. And then the scalp and hair conditions go undiagnosed or mismanaged at the primary care level. So that's where these models come in to provide specialist level diagnostic support to communities that would otherwise never access it. Then I'm going to talk about the problem statement. The problem statement is divided in two dimensions. We have the domain application problem where it explains that scalp and hair conditions are visually deceptive. This implies that you cannot just conclude that it's a specific condition just by looking at an image, because you have a condition like dandruff and a disease like psoriasis having show scaling in an image that is presented to the model. It would have an element of scaling, so we can't know if it's dandruff or psoriasis. Then we have alopecia areata and folliculitis. These ones show patchy hair loss, and it's also difficult to conclude that it's either alopecia areata or folliculitis just by looking at the image. So without trained specialists, we end up having misdiagnosis and delayed treatment, which may cause irreversible damages. Then for the computational problem, training models requires a lot of labeled images, and it's also difficult to find a model that gives a best balance of accuracy, efficiency, and interpretability for scalp pathology. So it's from this problem that we are trying to find a solution using the different models that we built. So for the next slide, we have a proposed methodology of how we are going to interact with the different models. So of course, our input is going to be the data set, which we sourced from RoboFlow. Then we shall have pre-processing, where we have EDA and then resizing of the images based on the different model that we are going to use. For example, EfficientNetB3 takes in image input of 300 by 300 pixels, while VGG-16 takes in input of 224 by 224 pixels. So we have to resize these images based on the model that we are going to use. Then we are going to train the different models, and finally we shall evaluate these models based on factors like accuracy, efficiency, and interpretability. Then moving on to the next slide, we have our first model, which is EfficientNetB3. So for this model, it's scalable and efficient, and it has 12 million parameters. It has 8 stages. Its key strength is compound scaling. So for compound scaling, it's explained in a way of, instead of making the model deeper or wider, we make the model scale depth, width, and resolution simultaneously. And this increases the accuracy of this specific model without heavy computational cost. Then I looked at a few research questions that are going to guide what we are going to focus on for this specific model. Then the next slide looks at the architecture for this model. So for this model, we begin with the input, which is a 300 by 300 pixel image input, which is followed by 7 stages of convolutional blocks. And these are mobile inverted bottleneck convolutions, which extract features efficiently using depthwise convolutions. Then next we have a squeeze and excitation technique. This technique amplifies the most relevant features while suppressing the features that are less relevant. So in our diagnosis, we look at those most relevant features because the less relevant features may misguide the diagnosis. Then we have global average pooling. For global average pooling, it compresses everything into a single vector, followed by producing the final class prediction. So the next slide tries to give more details of what I explained in the previous slide of the architecture, and then I'm going to look at the next model, which is VGG-16. My next model is VGG-16, which has a deep convolutional architecture that is heavier than EfficientNetB3. So for this model, we have a technique which is called GradCam. For this technique, it's a visualization technique that produces heat maps. And then these heat maps show exactly which regions of the scalp image drove the model's decision. So for this model, we are looking at the reasoning behind why the model made a specific decision. This model takes in 138 million parameters. It has 9 stages. Then in the next slide, there are research questions that also guided the key areas we looked at while training this model. Then this is the architecture for the VGG-16 model. It has, first of all, it has a repetitive architecture. What I mean by repetitive, it has 5 convolutional blocks, each with 2 or 3 convolution layers. So we just keep repeating between the convolution layers, and then for each block at the end of it, we have a max pooling layer that has spatial dimensions. And then it's also important to note that filter count doubles at each block from 64 to 128 to 256, and then finally to 512. At the end, we have output passed through 2 fully connected layers that you can see at the bottom of the diagram. Then I'm going to look at my next model, which is vision transformer, which is also called ViT. It has 86 million parameters and 8 stages. It has no convolutions at all, unlike the VGG-16 model. And then it divides images into patches and uses self-attention to understand the relationships across the entire scalp image. In the next slide, we look at the research questions for this specific architecture, and then for the specific model. Then this slide explains the architecture for this model. We have an input image of 224 by 224 pixels. This is the resolution of the image, which is divided into 196 patches, each of 16 by 16 pixels. So every patch has 16 by 16 pixels. And then we have a special token, which is called the CLS token. This token collects global information from all other tokens. And for this specific model, attention replaces convolution. Like I said, it has no convolution at all, like in the VGG-16. So for this one, we use self-attention. You'd look at it in a way. Okay, next slide. When I try to explain the architecture, you look at it in a way of you cut the scalp images into puzzle pieces, and each of these puzzle pieces is given a number. So we try to look for the relationship between these numbers that are given to the puzzle pieces, and that's how this model works. Then finally, I'm going to look at the DenseNet model. The DenseNet model uses a major feature which is called dense connectivity, where every layer receives output from all the previous layers. So it is important for differentiating between the conditions, since we are getting information from all the previous layers. And in the next slide, we have research questions that guided our key focus areas for this architecture and for this model. Then next we have the architecture. The architecture is a bit similar to the VGG-16 because we also have convolution, But for this one, we begin with an image input, then we have a 7x7 stem convolution, which is followed by the maximum pooling. It reduces the images from 224 to 56 pixels while computing the basic features. Then we have the dense block layers, which are separated by the transition layers. Each transition layer has a 1x1 convolutional layer, and then the four dense blocks have different layers respectively. For example, the first one has 6, the second has 12, the third has 24, and then the last has 16. They're separated by the transition layers. And then this is the architecture explained. Then finally, we are going to look at the key factors that differentiate all these models. So for the EfficientNetB3, we focus on its accuracy and efficiency. Then the VGG-16 has the GradCam. The GradCam is the one that provides the visualization of using the heat maps. So it's important for clinical validation to understand the model's reasoning. Then the visual transformer, ViT, focuses on self-attention, where the scalp image is divided into different patches, which you could look at as puzzles. Then finally, DenseNet, which uses dense connectivity, where the current layer gets information from the previous layer, so it puts all this together to get a final output. Yeah, that brings me to the end of the presentation. Thank you.